Continuing on Physical Chemistry Chapter 3, we're beginning Section 3 now. Now we're going to talk about an arbitrary cycle. So notice we've graphed pressure versus volume again, just like we did before. And we've got some arbitrary cycle here. It kind of looks like a circle, but it could have been a triangle. Nobody cares. So we've got some points along here. So we've got these dotted lines here. These are reversible adiabats. Now what we've done is we've connected a couple of points here diagonally through here. So this is a point on our arbitrary cycle. We've drawn a line through it, Mn, such that Mn is a reversible isotherm. And notice it goes all the way up to the two different adiabats. So this area under AB, that's the same as the area under AMNB. So what we can say then, remember work is PdV. So the work under AMNB, the work done by this process AMNB, is the same as the work done by just AB. So that's what we're trying to find here. For arbitrary cycle, we want to know the work from A to B, and we're going to do this by making up extra points so we can do the analysis. So the change in internal energy from A, M, and B is going to be equal just to the change in internal energy of AB. Now we know the change of internal energy is Q plus W. We've mentioned that 4 times before, I think. So QAM up here, this is an adiabat, therefore it's equal to 0. And likewise QNB, this dotted line is another adiabat, therefore this is equal to 0. And like I said, because they're both on adiabatic lines. So what that means is that the Q from A, M, and B is going to be equal to QAB, like we said before. It's going to be also equal just to the QMN. Now, the same thing at the bottom of the cycle. We've got points C and D on our arbitrary cycle, and we've got R and S such that they're both on those adiabats again. So we're going to say that the Q for RS is equal to Q for CD for the same reasons above. We don't have to duplicate it. Now remember, the cyclic integral for dq reversible over T is equal to 0 for a Carnot cycle. Now the Q over AB, that's from here to here, over T Mn plus the Q dc, so we're going this way around the circle, remember, over TSR is equal to 0. So remember, MnSR is a cycle. Where are we? MnSR. This is a Carnot cycle right here. So remember, the Carnot cycle is 2 reversible adiabats, that's the dotted lines, and 2 reversible isotherms, that's Mn and Rs. Now, how we draw it exactly doesn't matter. I mean, it could be like this, like this. Our scale isn't very pretty. I don't think it's actually a straight line anyway, but whatever. So we want to divide this cycle over here into an infinite number of these adiabats. So we're going to end up as TA is roughly equal to TB, TMN is roughly equal to T. Oops, can't read my own handwriting. Where are we? AB? Yeah. So we're going to just do stuff close enough that everything's roughly constant. TSR is roughly equal to T, DC, etc. So that is A right here. Temperature A, B. Now I can't read the B. Wonderful. Okay, so the dq from AB is over the temperature AB is equal to the dq dc over TDC. And remember, the reason the CD is backwards is because of the direction we're going around the cycle here. And that's equal to 0. So the cyclic integral, remember, dq reversible over T is equal to 0. So Q reversible over T is independent of path. Remember, this is a state function. So T is the temperature at which the heat is transferred. Now T, remember, this math to work has to be an absolute temperature such as kelvins. You can't do it in degrees such as Fahrenheit or Celsius. So remember, we had capital S as a state function called entropy. So we're going to say that ds is defined as dq reversible over t, and delta S is equal to q reversible over t. Now remember, work is an organized way of moving atoms, but entropy goes with randomness, not organized motion. So why are we talking about Q instead of work in this formula up here? Well, like I said, work is organized motion in the surroundings. It's orderly motion of atoms or molecules in the surroundings. Q, the heat transfer, is disorganized motion. It's disorderly motion of atoms or molecules in the surroundings. Now T takes into account the entropy that's already in the system. So if you have a high temperature, you've already got a lot of entropy in the system, and if you've got low temperature, you've got less entropy in the system already. Now adding heat at low temperature is analogous to a sneeze in a quiet library. Let's say delta S is equal to 100 kilojoules times, or 10 to the third joules per kilojoule over 273 kelvins. That's plus 366 joules per Kelvin. That's the units for extensive entropy. But if we do add the same amount of heat at high temperature, it's analogous to a sneeze in a noisy city. We're still adding 100 kilojoules times 10 to the third joules per kilojoule, but we're doing it at 373 kelvins, and we only increase by 278 joules per Kelvin. So delta S is equal to S2 minus S1, because it's a state function. That's equal to the integral from 1 to 2 of dq reversible over t. Now this is true for a closed system, for a reversible process. And any isolated system is closed, so that formula applies to an isolated system too. Now let's talk about delta S irreversible. It's equal to delta S reversible because S is a state function. For example, let's say you go from state 1 to 2. There's a reversible method here, an irreversible method there. You still end up in the same place, don't you? So delta S is going to be the same. Or put another way, if you have the entropy at state 1, the entropy at state 2, that's your change in entropy. You can do it the easy way with reversible, or you can do all sorts of funky stuff with irreversible, but it's just same end result. So S, remember, is an extensive property because it isn't, and it's also a state function. Now let's say we have a system with two parts here. So part 1, part 2. So there's dq1 reversible and dq2 reversible, both divided by t. So the ds for 1, this part 1 part of the system is just dq1 divided by t, and ds2 is equal to the dq2 over t. So the total ds is just ds1 plus ds2, or dq1 over t plus dq2 over t. And then again, that's because it's extensive. Now the change in entropy is equal to the change in entropy for part 1 plus the change in entropy for part 2. Or put another way, the total entropy is equal to the entropy from part 1 plus the entropy from part 2. So again, S is extensive. Now for comparison, density is intensive. The density of the system is not equal to the density of part 1 plus the density of part 2. That doesn't make any sense. Now the units of entropy, that's joules per Kelvin or calories per Kelvin. Now N is the number of moles. If you divide by N, you'll get the molar entropy. Then it's intensive. So the units of molar entropy is equal to entropy divided by N, so we get joules per mole per Kelvin, or calories per mole per Kelvin. And that's all for section 3.